each of these polynomials, since we're looking for that limit at either infinity or negative infinity, you really just need to start by knowing what the end behavior of the polynomial is. And for end behavior, remember, all we have to do is look at the term with the highest degree. So for that first one, all I care about is that that is an x cubed. And what that tells me is that, first of all, it's positive, and that it's an odd degree. Which then tells me that this graph goes from down to up. Our end behavior is down, up. And so then I can now look at what am I finding the limit of. The limit as x approaches negative infinity, so that's on the left side. And since that's where the down is, that means our answer is negative infinity.
Nice.
And we're going to approach each of these the same way. All right, next one. Again, I'm only looking at the term with the highest exponent. And so in this case, notice it's negative, and it's an even degree. Now, whenever it's an even degree, that tells me that it's either up, up, or down, down. Negative is down, down. So, of course, the limit then at negative infinity will still be negative infinity. All right. Then for the next one.
Don't call me names.
There. Our leading term, our highest exponent term, is the x squared. Notice it's positive and even. Therefore, we're looking at an up, up. And therefore, at positive infinity, it's going to be going up to positive infinity. All right, and for our last one here, the highest exponent term is the negative 5x to the fifth. It is negative, and it is an odd degree. That tells me that it is going up, down. So it's going up on the left, and it's going down on the right. In this case, since we're looking for the limit as x approaches positive infinity, that's where the down is. So it's negative infinity for our final answer there. So notice I can know each of these just by using the end behavior. Now, notice that's different from trying to plug in infinity. I don't want to try to plug in infinity into these because, for instance, with that last one, if I tried to plug infinity into that, I'd have negative 5 times infinity to the fifth plus 2 times infinity cubed. And by the way, we don't really do this. But if you were trying to think of it that way, you'd end up with a negative infinity from the first one plus a positive infinity.
0.
What does that equal? Because it doesn't equal 0. In this case, it happens that it equals negative infinity. But we only know that because of knowing the end behavior. We do not plug infinity back in like it's a number. All right. Now, today we're going to be taking some of those ideas and mixing them with ideas of rational expressions. And so, you remember we're rational functions? You've seen actually a few different types of rational functions, and actually last year and quite a few more. What are some examples of a rational function? Just any old equation of a rational function, please. We came up with a lot of examples here, but that last one, some of you are looking at that one and saying, wait, but doesn't that just equal 3x? 3x is not rational, but
3x over x.
the 3x squared over x actually would still be considered a rational function. And so, yes, that would still qualify. All of these are rational functions. And in fact, you've already seen some other rational functions this year already. You didn't like them much, but remember doing these types of problems?
18x.
Yeah, I know. You missed these, right? Let's call 11x minus, I'm just making up numbers there. But that's also a rational function. All of these end up being different rational functions, but they all behave slightly differently. Now, some of them, we hopefully know right off the top of our head how the graph would look. Like, all of these, we should be able to graph those, and actually even this one, without having to do too much. And actually, we could even graph that one, if we simplify it a little bit. Because all of those fit with some parent functions that we know. But the other ones, they get a little bit trickier. And so we're going to have to be dealing with what happens with these graphs. Specifically today, what happens with those graphs as we approach either infinity or negative infinity. So what are some of the possibilities? Well, thinking about the graphs, the 1 over x graph. Remember what that one looks like, right?
Like one of these.
Yep. So remember, that's the graph that looks something like that. Not that I drew it particularly pretty, but That's like the 1 over x kind of thing. What about like 1 over
No.
x squared?
No. One of those.
Remember what that one looked like?
Oh. Is that 0.1 or 1?
Either way, it would give us a graph that looks like that, where it's up on both sides. Because, of course, we're squaring it, so it never goes negative. Those we can know. But what about like that messy one where we had the x squared and the x both on top, and we had some x squared and we had some x on the bottom as well, remember, with different numbers in there, of course. What would the graph of that be doing?
Something a little bit.
What happens as it's going out to infinity?
Oh, it's still going up.
Well, there's some different possibilities, because like on these first two that we saw up here, you notice like as this one's going out to negative infinity, it's approaching the asymptote. Same kind of thing here. Same's happening as we approach positive infinity. It's approaching the asymptote. Okay. Does every rational function approach an asymptote? Well, remember one of our examples earlier? Would 3x squared over x approach an asymptote? No, because remember that equals 3x, provided that x does not equal 0. That one would actually have a hole in it, but otherwise it's just a line of 3x. There is no asymptote there. And what about if we graphed this?
Oh.
Does that have an asymptote in it?
No. Probably not. No.
Well,
That does that negative.
these are the pieces that we're going to figure out today, because there's really three main types of things that can happen as we're approaching infinity or negative infinity here. One is that they're both going the same direction, and so they approach asymptotes on the left and right. Another is they're going opposite directions, but still approaching an asymptote on the left and right. But the other is the oblique asymptote. And with the oblique asymptote, or you could also get a hole with this type of situation, notice that as you go out to infinity or negative infinity, it's approaching infinity or negative infinity. And so we need to be able to know which is which. And that's what today's work is going to be about. I have some formal notes for you to take. So please add this into your notes. So now that you got it in your notes, let's make sure you really understand what it is that you actually wrote down on it. Because there's a lot of detail in here, but being able to read these mathematical definitions is part of what we have to be able to do. So notice it starts by basically saying that we have two functions, one over the other. So all it's done then is just say that we have some polynomial over polynomial. That's basically all it said there. All right. Now for the two polynomials, though, they say that the leading terms are ax to the n and bx to the m. Basically, that the top function has degree n and the bottom function has degree m. They just defined all that stuff so we'd know what we're talking about with n and m down below there in the rules. So you notice like that first one, if n is less than m. Okay, was n the one on the top or the bottom?
Top.
The top. So that's like basically then if the top exponent is smaller than the bottom exponent, so like the function is bottom heavy, then that means that it's going to have a horizontal asymptote at y equals 2. It'd probably be easier if we just said it was bottom heavy there, right? But this is a formal definition. Okay, the second one, if n equals m. Basically there it's just saying, okay, in this kind of a case, if the top and the bottom have the same degree. So they're balanced, in other words. But there, notice your horizontal asymptote is actually equal to a over b. Hence another reason why we have that formal definition up above. Notice that a is the coefficient in front of the highest degree term on the top and b on the bottom. And so we can actually then know that the asymptote there is going to be at a different number. And then on the bottom, the third one, well, that's just saying like it's top heavy. It does seem like it'd be easier to remember, though, is like bottom heavy, balanced, and then like bottom heavy and top heavy, right? Okay, so perhaps then you might want to add that into your notes that you took on it as an easier way to remember it. Following this, we're talking about where the asymptotes are, and I just need a formal definition then of an asymptote for you. So a horizontal asymptote, notice, occurs when our limit as x approaches infinity equals that number, or as x approaches negative infinity. Because remember, we've seen functions in the past where it has an asymptote only on one side. It doesn't have to be on both sides, like an exponential, for instance. And so this is just a formal definition of horizontal asymptote that we're going to be using going forward. So for that first part, we notice, first of all, that the degree of the bottom is bigger than the degree on the top, because it's 1 on the top, 2 on the bottom. So this is a bottom heavy. We check our notes, and you can see the bottom heavy says the asymptote's at 0. But remember, we don't just say the asymptote is at 0. The asymptote is that horizontal line that it's approaching. We have to actually say that the asymptote is at y equals 0. Yeah, you got to include that y equals. Now, once we know where the asymptote is, then we can evaluate the limit as x is approaching infinity. Well, as we go out to infinity, obviously we're going to be approaching the asymptote. That was the point of that last slide and that last set of notes. And so, the limit equals 0. So for the first one here, remember that the only things that determine the asymptote here are the highest exponent terms on both the top and the bottom. So as I look at the top then, that means the 2x squared is the only thing that I care about, and on the bottom, the x squared. Everything else is just extra information that's not going to affect anything here. Alright, so notice that the two exponents are the same. That means we're in the balance scenario. Now in the balance scenario, the asymptote is at a over b. A is the coefficient on the top, and b is the coefficient on the bottom. So that means it is going to be 2 over 1. So the asymptote then is at y equals 2. Which then means that when we evaluate the limit of the same expression down below there at negative infinity, it has to be approaching the asymptote, so it's approaching 2. Alright, and the last one. Again, all we're looking at is the highest exponent terms. So the x to the 5th and the x cubed. In this case, you'll notice that it's top heavy. Okay, that means there is no asymptote. Well, if there's no asymptote, then how do we evaluate the limit? Because we still can do it. Well, what you end up doing is you actually just treat it like a polynomial and you simplify it first. So I take those same two, the x to the 5th, over x cubed, and I'm going to simplify that. And so that simplifies down to be x squared. What is the end behavior of a positive 1x squared?
Up.
It is up, up. Alright, so now I can actually evaluate the limit as x is approaching infinity. So that's going to the right, so that is a positive infinity. So there would be our limit. So since I can give you now a fraction, a rational expression, and you can tell me what the limit is, now write your own that gives these limits, please. And yes, 4 separate functions that you're going to be writing here. So for number 1, we need a limit as x approaches infinity that will equal 0. Notice that just tells us that it needs to be a bottom-heavy rational function. So as long as the bottom has a higher degree than the top, you're going to be fine. It can be all sorts of things, and you can put all the numbers in there that you want as long as the bottom degree is higher than the top degree. All right, for number 2, our limit as we approach negative infinity is at 3. So we're definitely approaching an asymptote, but in order to put the asymptote at 3 instead of 0, you have to have a balanced equation, which means your top degree has to be equal to the bottom degree. So that means we might have something like x squared on both the top and the bottom. But if I just did that, that would have a limit at 1, because it's 1 over 1. I want the limit to equal 3, so I need to put a coefficient in front of that x squared, like 3x squared. Or if you want to get extra fancy, you could do maybe like 6x squared over 2x squared, something like that. One little detail with this one though. It's a tiny detail, but it's worth mentioning. That we wouldn't want to just say, for instance, 6x squared over 2x squared. Because that one would totally reduce down and it would just equal 3. Well, actually, we could even do that, couldn't we? Because that one would just simplify down to be a horizontal line.
Whoa.
And so you can see it actually still works, right? All right. Next one. Same basic idea, except in this case, we want that limit to equal -2/7. So again, balanced on top and bottom. So for instance, I'll call it x to the 5th this time and x to the 5th. And you can throw in all the other kind of stuff you might want to on that one. But I need to have a 2 on the top, I need 7 on the bottom, and I need at least, actually I need one of those to be negative. So like, I could do -2/7. Could I make them both negative?
No.
No, because the negatives would cancel each other out. It'd be positive. All right, great. Last one, 4. In order for our limit to be infinity, that means it has to be top heavy. And so we need to set up some scenario where it's going to be like x cubed over x or x squared. Basically, the top degree just has to be bigger than the bottom degree. So that would work. It's kind of basic, but it would work, that sort of a thing. But then all that does is tell me that it equals positive or negative infinity. I need it so that it equals a positive infinity. Now, that particular example wouldn't work. X cubed over x, you notice that would simplify down to just equal x. In the graph of y equals x, well, at negative infinity, that's at negative infinity. You need something with an end behavior that starts with up. And so then I might change my x cubed over x squared into just x cubed over x. Because that is then an up for its end behavior. Something along those lines. The other way you could have done it is you could have done it with squared, but then made it negative. Because that has an end behavior of up, down. So lots of different options for how you could have done any of these.